This meeting is being recorded.
Can everybody hear me? If so, then we can get started. Okay, awesome. Okay, so today's class will be on complex numbers. This lesson's by me and Andy. So let's start with the first section. What are complex numbers? Complex numbers are an extension of real numbers that include a mysterious unit I, which is defined with the equation I squared equals -1. Obviously, if you've done some math, you know that a square of a number can never be a negative number. And that is why we call it an imaginary number. 1 second. Okay, you can see that this value doesn't have a real logical value and are called imaginary numbers. Complex numbers are any number that can be written in the form a plus bi, where a and b are real numbers. Basically, this is just a real number here plus a complex number. And as you can see, this would encompass all possible numbers, real or unreal. Since imaginary numbers are when a equals 0, or when it's just a term times I, and when b is not equals, then and when b is equal to 0, then we just have a, which would make this a real number. A complex conjugate is denoted as z, where z is a complex number with a bar over it, and that is just denoted as a minus bi, when z is equal to a plus bi. And that's pretty much the basis of what complex numbers are. Let's get started with some very simple introductory problems. So these are just like computational. So just maybe send the answer in the chat, and when enough of you get it, then we can just like move on. I'd say try the first four for now. Oh, and I can send the PDF of this on the Gmail link so you guys can follow along on your own device. Okay, so if you check the email with last AIME workshop section 7, then it should have the complex number handout as well. I'm trying to figure out how to make myself not have pig ears. There we go. Can you guys send the answers in the public chat? Because I'm trying to follow along on another device. The one with the host ID is just displaying the handout. Okay, yeah, awesome. It seems a lot of you are getting the gist. I have 3 submissions so far. Let's wait for one more before we move on. And if you're done, you can maybe try like the fifth and sixth problems are not that bad either. Does anyone have any questions about the first four problems, or am I okay to move on? Okay, I'm gonna take the silence as a yes. Problem six should be pretty fast, and problem five, maybe I can do the pretty disgusting computation. So when you work with complex numbers, very um uh, identical sorry, what am I saying? So when you have complex numbers in the denominator, such as in this term 2 over I plus 1, we can use the factorization of a squared minus b squared equals a plus b and times a minus b to multiply this by its complex conjugate to get a times 2 times I minus 1 is over I plus 1, I minus 1. And since this is a fraction, these two terms are identical. And we just get 2I minus 1 over, and we use this to get this is I squared minus 1, which is just equal to negative, this part's equal to negative 2, and this whole thing is equal to 1 minus I. And we can use the same thing for the second part of the expression, 9I minus 7 over 2I minus 1. And we, like it's the same thing with square roots. So in square roots, you say you rationalize the denominator. We're just basically turning the complex, the denominator of the fraction into a real number by multiplying by 2I plus 1. And this is just negative 5. And we can just take away the brackets here to get negative 25 and negative 5I, which makes this equal to 5 plus I. And when we add 1 minus I plus 5 plus I, and we get our final answer of 6. I see many of you got this in the chat. That's very cool. If you know the definitions of these words that are listed above, number 6 should be relatively easy. As if you just have z plus 1 is imaginary, then we know the a is just negative 1. And if z minus 3i is real, then we just get b equals 3i. Our z is equal to negative 1 plus 3i, and we just have a plus b equals 2. That should be fairly trivial. For number 7, similarly, we use the real and negative. And actually, wait, let me work this one out. If we know that m plus n is real, then we have that the I terms, when they're added together, there should be I there. Sorry, that's my bad. And when they're added together, they should be equal to 0. So we have negative b squared minus 3b minus 2 plus 10b plus a squared minus 3 equals 0. And we can combine some like terms into getting negative b squared plus 7b minus 5 plus a squared equals 0. Now when we add the real parts, something magical happens, and we get 2b squared minus 14b plus a. minus 45 equals 0. And we can see this term of negative b squared plus 7b is just multiplied by negative 2 in the second expression. So let's just say negative b squared plus 7b is equal to c. We get c equals negative a squared plus 5, and negative 2c equals 45 minus a. And also we know that this is not, oh, sorry, it's not equal to 0. This is negative. So the real part would just be less than 0. Sorry. Less than 45. So now we can represent c in terms of negative a squared plus 5 to get a quadratic. We get 2a squared minus 10 is less than 45 minus a. Let's move to some terms to the left. We get 2a squared plus a minus 55 is less than 0. And this is just a basic quadratic that can be factorized as a minus 5 and 2a plus 11. And if you're familiar at all with algebra, then we can just see that the minimum value for this is just going to be a is equal to negative 11 over 2. Wait. Huh. On my screen, it says this is non-positive. On the solution screen that I'm pulling up, it says non-positive. So that would make this a valid case. So yeah, sorry, ignore this. This is non-positive. So we don't just have a hole where it's like infinitely great small value greater than negative 11 over 2. Does that make sense? Does this make sense, guys? Or is there a specific part you want me to go over again? Okay, I'll take a silence as a yes, and we'll move on to the next section. So to represent complex numbers, we can use a complex plane, and that looks something like this, where the x-axis represents real numbers. So this would go like 0, 1, 2, 3, and negative 1, negative 2, negative 3, like a normal number line. And the y-axis represents imaginary numbers, where this would be I, 2i, 3i. This would be negative I, negative 2i, minus 3i. And so then we can see that on this axis, we could plot any complex number a plus bi by choosing the value of a on this and the value of b on, say, on the y-axis. And where those two lines meet will be our complex number z, where z is equal to a plus bi. So it's basically like a regular Cartesian plane if the y-axis is just like multiplied by a factor of I. Now we can define this new term, the magnitude of z. It's kind of like vectors. And the z magnitude is the distance from z to the origin of the complex plane. And that's just denoted as a squared plus b squared rooted when z is equal to a plus bi. Does that definition make sense? Okay, awesome. Okay, now this is section 2, and Andy will explain this part. Andy, can you screen share, or do you want me to leave this up here?
You can use a screen share.
Huh?
You can use the screen here, I guess.
Okay. I'll try to
Okay.
take notes.
So let's solve this. Wait, so like wait, should I like okay, whatever. Wait, I can't annotate. Alright.
Oh, how do I do that?
Wait, I'm also not coast. I'm coast.
Huh?
Also, you're supposed to admit two people into the
Oh, there's a waiting room. Do you want to just share your own screen and maybe you can annotate on
I don't
that
think I can
because
share
I'm
it
not
now.
sure what buttons I'm supposed to press. Okay, well, do you want me to just like attempt trying to take notes?
Sure. Okay.
Okay,
So now we
we'll
can
do that.
after having complex numbers, we can take a look at quadratic equations. And so like usually like you've been taught that if we have this discriminant b squared minus 4ac is smaller than 0, then there's no real solutions. Which and emphasis on real. Because now if we have complex numbers, we can still take the square root of the discriminants. And we instead of having so instead of getting a real number, we get complex numbers as the solution. And so, for example, and so actually this works because if you go through the steps of the deriving the quadratic formula, you take the square root at some point of the discriminant or like over 2a and stuff. But and so that step is actually valid. And like we can make it explicit. For example, in question one is really simple. Because we have x squared plus 4 equals 0, then if you move 4 to the other side, then we get x squared equals to -4. You just directly take a square root, right? And for number two, however, like we can rewrite it as x plus 1 squared and plus is equal to -1. And that's like exactly how you derive the quadratic formula because you're going to be completing the square. And so you get x plus 1 squared, x plus 1 squared is equal to -1. And so if you take the square root of both sides, where you get that x plus 1 is equal to I or -I. And and this gives you the two solutions. X is equal to like I minus 1 or x is equal to -I minus 1. And so should we let them solve problem 3 or like should I just
Yeah, maybe let them do 3 and 4. They shouldn't be too
so you
bad.
guys should try number 3 and 4. And like it's just how I did it. All right.
Wait, is that correct?
I don't think so. Because you're missing the real part,
Yeah, I'm pretty sure there is a real part in this one. Wait, no, it's guaranteed to have a real part. What am I saying?
I guess. Sure. I'll take that.
Okay. Where is my? Oh yeah, that should be correct.
All right, so yeah, 2 plus 9 equals 3. I so we solved the equation x minus 1 from problem 4. Yeah. Oh yeah, you guys should also think about problem 4 if you guys finish problem 3.
There we go. For number 4, if you know how to solve cubics, it's like the same strategy to find like a smaller root and then factor it into quadratic.
Wait,
Yeah,
say
exactly. For problem 4.
I don't. Wait, do any of you guys know, like, this is extremely rare, like, do you guys know how to solve any cubic, like the cubic formula, or like
Oh my god.
like
Don't use the cubic.
like exists, but like
It exists, it's so real. Oh, looks like Shreyas has also got the answer.
who?
Shreyas Sane.
I wonder who that is.
I wonder who that is as well. No, it's not that big. Oh, the cubic formula? Oh yeah, the cubic formula is really big. I looked at it, I'm like, oh yeah, I'm not using that.
Well, you guys can use it. You guys should wait. Like, this is like not very related. Like, by chance, it's also a good exercise, anyways. Like, you just learn how to like solve a cubic, even if you don't have a formula. Because using formula is bad, but like if you know how to solve a cubic, I don't know.
Okay. Well, it seems enough of you have gotten the answer. Maybe we should move on.
Yeah. The number 4, you factor x minus 1. And if you factor x minus 1, you use synthetic division, or like you can, right? And afterwards, you just, yeah, you get whatever that man's writing. And this over there, you can write it as, you can also complete the square. But yeah, quadratic formula, and then discriminates like whatever and whatever. 36 minus 60 and stuff. And eventually you'll get it.
I have the answer here. It's 1 and 3 plus minus root 6i. So good job if you got that.
But the details are left as an exercise to the reader.
Which is just plugging the quadratic formula on these numbers. Which
And
is
so no advertising in chat. Okay. Anyways, so we can also use this on higher degree polynomials, and it's exact same. In fact, there's this thing called the fundamental theorem of algebra. Although it's not fundamental, it's not a theorem, and it's not from algebra. Ignore that. So like any polynomial n has exactly n complex roots in counting multiplicity. And so the other important thing is if a plus bi is a root, then its conjugate also must be a root. This is actually like sort of non-trivial. So you guys should try proving it, but we're not going to do it here.
you can prove it like easily for like smaller cases, like a quadratic. And for that, you just use Vietas. And
It is from the form of the quadratic formula because like it's plus minus equal square root of something. And square root of
that works
something
as well.
is the only thing that gives you imaginary.
Yeah.
And okay, so do number 1. It's pretty simple actually.
I feel like 1 and 2 should both be okay, actually.
Wait, Eric, did you make a mistake? Oh wait, never mind. I'm being dumb. Oh yeah.
Oh wait, why is this like not the most updated form? Am I like tripping? Or is it like on this on both? Huh. I think I just like didn't revert some changes on the solutions to the actual thing. Okay, whatever. It shouldn't really make that much of a difference.
All right. So have solutions coming in chat, maybe
Alleged.
allegedly.
Yeah, that's good.
It is.
Yeah.
Okay. So we can just find A and B individually. A by Vieta, it's a negative of the sum of the roots. And we already know that. Oh yeah, we have to realize that 4 minus 3i is also roots by our theorem. And so A is negative A and B is 4 plus 3i times 4 minus 3i. And this is like just a magnitude squared. And that's going to be 25. So negative 8 times 25 is negative 4. Okay, on to problem 2. You guys go.
Yeah, so far I don't think the problems have been too bad, but they get worse later.
Anybody think number 2?
There are some problems on the solution document that is not on the real document. I'm very confused.
That's your problem.
Yeah, I'm gonna move them over. Maybe I'll send like another PDF at the end. But it's like a very trivial problem anyways. I think it's okay.
Oh wait, are you guys challenged by number 2?
Oh no, wait.
I think it is that simple. Eric?
Yeah, so either.
Huh?
I'm pretty sure it is as well.
Yeah. So basically, very important fact you guys remember the product of the magnitudes is equal to the magnitude of the product.
That is a very cool thing to remember.
Yeah. And we know that we know that the product is 32 over 2 by the end of 16. So it's absolute value of 16, which is 16. Okay, number 3. This is a bit harder.
Yeah, number 3 is a bit harder. But yeah, that is a really important thing to know, that magnitudes are multiplicative, and also the magnitude of a complex number z can also be equal to z times the conjugate of itself.
Ah,
Oh yeah, z squared, my bad. How are we doing on time? Oh, I think we're doing okay.
Wait, legit, if I just solve the problem, I just like write n equals like a plus bi and n equals c plus di and bash.
Yeah. That is basically what the solution is, actually.
Yeah. That's guys, that's always your last resort if you see complex numbers like that.
I think that's what I did to solve the complex number one on the AIME this year. Just said
Hell nah.
that one with like I think it's in I think it's in like the applications section actually, or maybe it's in the homework. But I just
But yeah,
yeah. I don't want to hear it, Shrez. Solve the problem.
Wait, wouldn't Shreyas hypothetically know what complex numbers are?
No, I'm pretty sure he doesn't.
sorry, I was watching YouTube shorts. That's my bad.
Okay. Yeah, if you just plug his a plus bi and like c plus di, and then the other root would just be what would the other root be? The other roots would also be a minus bi and c minus di because of the fundamental theorem of algebra. Because we know that the real parts are not equal, so these all must be distinct. And we just have our four roots of our cube of our quartic. And when you multiply them by I, the roots of this are just going to be negative b plus ai, b plus ai, negative. Wait a minute. Um. Okay, wait. I think it's okay.
Yeah.
Because what was concerning me was that these would have to be conjugates of each other.
I don't know. Wait.
Because these do
Yeah.
have real coefficients. So I'm pretty sure it just works out.
Yeah. No, but yeah, because like on the second one you can also figure it out.
Honestly, though, if we just like do the first Vietas, which is just like the sum of the roots, we just have like 2 times a plus c equals -6, and times b plus d. A -2 times b plus d is going to be -8, and I'm pretty sure it's going to be 8. Sorry, and I'm pretty sure it doesn't even matter that these are conjugates and they're like and what that means, we just get the a plus c equals -3, b plus d is -4, and to find the magnitude of n plus n is going to be a plus c squared plus b plus d squared rooted, and we just plugged in these values, and that's just 3 squared plus 4 squared rooted. That's just 5. I'm pretty sure I wrote this problem, so the numbers do work out. But this is really just a paper tiger. If you know what you're looking for, it's really fast. Just use Vietas on the sum of the roots. Does that make sense?
Wait, how do you get 2a 2a plus c is -6 again?
You just use the sum Vietas for both polynomials. Let me erase some of the bubbly lines. So
Right.
for the first one, you get just use Vietas on this term, so you get -6 is equal to wait, I erased these. The real parts of that's just some of these things. I said their conjugates is just 2 times a plus c. Yeah.
But you aren't given that wait. Oh, never mind.
And when you multiply by I, you just get the real parts as negative b and b and negative d, negative b, negative b, negative.
Okay.
And then yeah, it's the same thing for the second one. So you get the b plus a plus c and b plus d.
All right. Now, should we just move on?
Next session is polar form.
And
So
you
I think I
win.
can do this one, yeah. So a polar form of a complex number a plus bi. First, we can just map it onto the complex plane here, and we can write this as also as its distance to the origin. We can let that be r, and its argument to the origin, which is just the angle between the x-axis in that line, and this is theta, and theta ranges from 0 to 360 degrees as it goes like completely around the circle. It's kind of like a unit circle in trigonometry. It's kind of like the same idea. Oh my god, it's a horrible circle. It's just like the unit circle in trigonometry. It's just kind of the same idea. Now to rewrite this, we can write this using the same idea as a unit circle. We can write it times r times cosine theta plus I sine theta. And we can think of the r term as just like projecting this term outwards. So when we divide by r, we just have some term exactly on the unit circle because we're dividing by both the real part and the imaginary part. And for this point on the unit circle, it's just the same idea as a unit circle of trigonometry. It would have coordinates cosine theta, sine theta, and since this is a complex plane, it's just going to be cosine theta plus I times sine theta. And we can also write this as r times e to the I theta. I'm not sure why it's e to the I theta, but that just like basically means this, where cosine theta plus I sine theta. And that's just how you denote it. Another way you can write it is r times cis of theta. And cis is also just a constructed term. Normally nobody uses cis as often. I'd say this is the more often one that's used. Try to remember this one. Does that make sense? Okay, awesome. Okay, so using this idea of maybe I should do, where do I have some space? Using this idea of representing it as r times cis of theta. Oh, I said it wouldn't be used as often, but I think I'm using it here because the latex is just much better to write cis of theta than e to the I theta. So we can show that when you rotate a couple, we can use complex numbers in rotations, where let's say you wanted to rotate some point by a by b by some degrees, let's say theta degrees. So first we want to map this onto the unit circle, and to do that well wait, first we can represent each of these terms as r1 sine cis of theta 1 and then r2 cis of theta 2. There should not be an extra 2 there. And we can first map out the r1 r2, and we do r1 r2 times cosine cis of theta 1 cis of theta 2. And we can think of cis of theta 1 as a rotation of theta 1 degrees around the origin, and cis of theta 2 as an additional theta 2 degrees, and this is theta 1. So what we're really rotating by is cis of theta 1 plus theta 2. And that is just what this is. And that is basically how you rotate complex numbers, where the thing you rotate from, you want it to equal the origin. And that's basically what we're doing in this theorem here. We're first going to subtract, you first subtract the c minus ci and minus di to move like this point b to the origin, like translate it. And every other term, let's say a, would also get translated along with it. And then we do the cis of theta rotation, and then we translate everything back up again. I know it's not a very good definition, but if you search up complex rotation, it will basically just be what I am saying here. So enough of me yapping. Let's just work through some problems. And maybe if it's unclear about the theorem, we can work through an example together and maybe it make more sense. But
That's
really,
my problem.
huh? Oh, it is your
Number three.
problem, Chris. Wow. Okay. So number 1 and number 2 should be okay. I can go through number 3 because number 3 requires some ideas. But if you know the ideas, then it should be pretty trivial. We can think of e to the theta as just a rotation of 2 pi I3 over 3 around the origin. And maybe that'll help make you visualize the problem better. And using this idea of rotation for the second problem, we can see that when you rotate something by, let's say, 2 pi, it becomes exactly the same. And when you rotate by the negative of the angle, which is going the opposite direction, it's the opposite value of, it's a conjugate of the original value. Okay, I think we're all pretty sure on the first problem. So I think I can move immediately to the second one. So for the second problem, let me see what I have here. Okay, so we could see that when you rotate by something, let's say you're rotating by theta degrees, and you rotate by another pi degrees, which is 180 degrees, it just goes to the completely opposite value when it's 180 degrees. Oh, so you get that e to the theta I theta plus e to the I theta plus pi is equal to 0. And we can see that's exactly what these two terms are, which is just another rotation of pi degrees, so they cancel out. And e to the 12 pi I over 7, we can subtract this by 2 pi, which is the full rotation, to get this is equal to e to the negative 2 pi I over 7. And that's exactly what this is. So the answer is just 2 e to the negative 2 pi I over 7. Does that make sense? Okay, awesome. Now for the third problem, it requires a very nifty observation. And the solution is actually really nice following that. So for the third problem, you have that, wait. Okay, yeah. So let's say when you rotate something by theta degrees, if you rotate by 360 minus theta degrees, when you wait. Yeah, 360 minus theta degrees, it ends up exactly on the real axis. So if let's say you rotate a complex number in a unit circle by theta degrees, and if you rotate by another 360 minus theta degrees, it'll just go exactly to 1. So what we have here is that e to the 2 pi I n over 9 times e to the 360 degrees, or I can say 2 pi 8 times 2 pi I over 9 times in, then this will just be 1. So we can have that for any e to the 2 pi I n over 9 is just equal to 1 over e to the 16 pi I n over 9. Does that make sense? So what we're basically saying is that sum e to the I theta times e to the I 360 degrees minus theta is equal to 1. And yes, that is basically the same thing as rotating by negative theta degrees, because we could just subtract 360 degrees from here. Oh, I guess that is a better way of phrasing it. But it doesn't really matter. So we can just use that in this problem. So for any pair 1 over 1 minus e to the 2 pi I n over 9, we can see this goes from 1 to 8. So we could try to think of pairing up, let's say 1 over 1 minus e to the 2 pi I over 9 plus 1 over 1 minus 2 pi ai over 9. So what we have here is that e to the 2 pi I over 9 is equal to 1 over e to the 16 pi I over 9. So we can just substitute that in here to get this as e to the 16 pi I over 9 over e to the 16 pi I over 9 minus 1. And what we're basically doing is substituting that in here and then multiplying by e to the 16 pi I over 9. So now we just simplify this expression to this plus 1 over 1 minus e to the 16 pi I over 9. And that is just e to the 16 pi I over 9 minus 1 over e to the 16 pi I minus 1, which is just equal to 1. So we see that every pair of n and 9 minus n, they just become 1. And that's just really cool because we just have 4 of these pairs for a final answer of 4. Does that make sense?
Such a great problem, right? Thank you. Thank you.
Chris wrote this problem with ChatGPT, and I thought it was really good because it had such a nifty solution, so I just kept it in.
Don't tell me this.
Lies.
He absolutely did. I watched it. But it is a really nice problem. I liked it. Does this make sense to everybody? And I think now we arrive to some rotation bashing, with lack of a better term. Rotations are important, but I do agree that they suck to write out because it's really hard to have like some degree rotation around 2 points and they all have like nice numbers. So these problems are going to be a bit painful, but hopefully I picked not too bad numbers. And what you just do is basically just apply the rotation formula on 4 and 5. 5 is a bit trickier, so I think we just start with 4. And since it already starts with the origin, we can just think of multiplying by, oh, it says clockwise here. So keep in mind you're rotating by e to the I 240 degrees. I think for the interest of time, I'm just not gonna go over number 4 because number 4 is just a basic theorem application problem, and number 5 uses what you do in number 4 to solve a, I'd say, more complex problem. So I'm just gonna go over that one. So if we have when you rotate 1 minus 2i by theta degrees counterclockwise, you put it on the origin. So you have 1 minus 2i, and when you multiply this by e to the I theta for thumb theta, this just becomes the magnitude of 1 minus 2i, which is equal to square root 5. And so what you have is e to the I theta equals square root 5 over 1 minus 2i. And now when you want to rotate z by z I e to the I by theta degrees, sorry, you multiply this should all be z by e to the I theta. And this is just equal to root 5, 1 minus 2i times 3 plus 4i. So you just want to simplify the complex number 3 plus 4i times square root 5 over 1 minus 2i. And we've already gone over how to simplify complex numbers. So you just multiply by 1 plus 2i to get on both sides to get a final answer of, let me see. You get a final answer of, actually, I'll just calculate it. This is just 5 over root 5 times negative 5 and plus 10i. So what we really have here is negative root 5 plus 2 root 5i. And so the sum of the, okay, so what we have z to be is just negative root 5 plus 2 root 5i. Does that make sense? Okay, I think that should be good. Andy, do you want to start section 4? I think we have half an hour left.
Sure. Okay, we're going to talk about roots of unity, which are very interesting. So, roots of unity are basically numbers that satisfy x to the n is equal to 1, right? And there is, you can see where the name comes from because roots are like the solutions and then unity for 1, right? And now, so like, as the screen says, we have the roots of unity are like some form of e to the I times 2 pi k over n for some k, where like n is the like the number of the roots in E. So like we refer to them as the nth roots of unity. That's usually how you refer to them. And so equivalently, we can multiply the root. We can multiply like and no wait, not multiply. We can rotate some certain points, and to get whatever we want. Right, slow down.
Yeah, because when you rotate something by like e to the 2 pi I over n, then when you take the n power of this part just becomes e to the 2 pi I, and that's just 1. So you can just rotate it by this, and you get all the solutions.
Yeah. Okay, go.
Okay, yeah, sorry.
And here are some problems. And so the first one's pretty simple, just to test what you've learned. So you guys should solve this in like 10 seconds.
I'd say the first 4 are okay, but these are mostly just like, yeah, testing problems. If we go over something, I'll probably go over like 5. And the ones with stars, I wouldn't say they're bonus. I just say they're a bit harder, and they're maybe like, I think I style them to be around like AIME number 9s, I'd say, or like 7s to 9s.
All right. The problem 1 you guys have already solved. Yeah. Yeah. And so for these problems, you can also represent in polar form.
Yeah.
Yeah.
Polar form, I think would
You
be.
didn't know your answer isn't not correct. It's like, all right. So you guys have to remember very important to remember the values of the third use of unity. They're 1, -1/2 plus √3 over 2, and -1/2 minus √3 over 2. Wait, Eric, could you like draw the quick diagram of the?
Yeah.
Yeah. It's like the real parts are both -1/2 for those two. And you sometimes see them as omega, written as omega and omega squared. That's like pretty nice. And yeah, somebody has to solve the second problem. For the problem, you just take the cube root and like, oh yeah, important thing in complex numbers is you don't have something like a well-defined cube root or square root. Because like, and it actually like, for example, if you take the nth root, you have n, like if you have n different solutions. And they're actually all, for any solution, for like if you take one particular, that's a bit abstract. We're like, take the like nth root of like say fifth root of 7, for example. And there's and like in real numbers, you're gonna get one number, but like in complex numbers, you get 5 different solutions, right? In fact, if you take any one of the solutions, the other 5 solutions are that solution multiplied by the not like the fifth roots of unity that are not 1. And so that's super cool. Like that also illustrates like why you can't just say like for like third root of unit like cube root or square root or something. And, like you're gonna have other things that go wrong. But anyways, back to this. Yeah, it's like yeah. Number 3, yeah. Number 3, you guys can quickly solve it. It's just 0 because there's a factor of x squared you can divide out of both sides. Afterwards, it's just the 4th roots of the unity, which are 0, which is 1, I, -1, and -I. Pretty simple.
Wait, Andy, would this only have 5 roots then?
Yeah.
Wait, then the 6 power. Wait, I'm actually like tripping. Why is there a 6 power then? It's like,
Because there's repeated root of 0.
oh. Oh yeah, because like x squared equals, okay, yeah.
Okay, so number 4, you guys might need some time to think about it. Pretty interesting.
I remember where I did complex numbers, like it was kind of new, and I don't think I understood anything in the first class, but just from like looking at it a lot, or like on AOPS forums or like websites where I just like read the solutions, I think it started like clicking gradually.
You guys should definitely read was it AOPS? To think on AOPS about it. It's gonna really help.
Yeah, Vincent's got it. Vincent knows a very cool idea for 4. I think I want to get to applications and my really fun bonus problems. So I'm gonna like, I think we should like explain them.
All right. For number wait, how'd you do number 5 easily? I guess I don't know. I like so yeah for like the first equation it's like that, but the second equation is not. I don't know. It's factorizable, so I guess
Yeah, it's factorizable as well. Yeah. You can just like factorize these terms. Or x 2x minus 1, sorry.
Yeah. Number 6. Wait, sure. You guys want? Do you want them to move on to number 6?
Your choice. I don't really mind.
All right, number 6 is very nice to think about. I mean,
Now
it's
think,
not hard,
now think about it.
huh?
And just like, yeah, think about it.
It's not hard. It depends, actually.
No, yeah, I think it's okay. Yeah. Oh wait, it should be x minus 1. What am I doing? Oh wait, this is just how you solve 5. You just have this condition where this is not equal to 0, and we have that x equals 0 or x6 equals 4. And if we have x6 equals 4 to this be true, some of the solutions will have x cubed equals 2. So we want the solutions of this to have x cubed equals -2. And I'm pretty sure these all work. Oh, and x equals 0 doesn't work because then x squared is 0. So we only have like a few solutions here, which are the solutions where x cubed equals -2. And to do that, we just like use what we've done with here for these previous problems, and that's just how you do number 5. You have to write the cube root of -2, which is like a little annoying, but it's just like a very, yeah. Yes. Andy, do you want to do number 8 or do we just move on to applications? I don't really.
I know, right? What?
You want to just do applications? I don't really mind.
I think they should still look at number 6. It's not
Okay.
that hard. Like, but I don't know. Can we use a squared? What do you
Honestly,
mean?
that might be smart.
Huh?
Wait, honestly, is that smart? Wait.
Wait, I don't see how that works. But like, whatever. We gotta see.
No, but if you do that, you can only just like factorize it once, and I'm pretty sure it becomes like still really nasty. I'm not sure though. Maybe it works.
You could try.
Or if we do that, it's like x4 plus 3 x minus 1 to the 4th I.
Like,
So this would have to probably be like 0 as well, right?
wait, I don't know. That's
I'm not sure. It's a little like freaky.
right to me, but I don't know.
Or no, it wouldn't have to be 0 because at the
No.
end you're just like multiplying by another thing, and that makes 0 at the end.
No, but then you have like a polynomial with imaginary coefficients. That's not nice.
Yeah, that is not nice. Yeah, maybe we should. Yeah, I think I'd say keep your coefficients real. Just move x. Just turn it into x8 equals -3x minus 1/8. And wait, let me see what we have here. And then you divide by this equals x over. I'm just reading what Andy put on the x minus 1 to the 8th equals -1. And we can solve this like the strange factor we solved number 4. And for each of those, we can find x. It's not the very nicest problem, but it gets the point across
It does?
marginally. Yeah, honestly, this is not a very good problem. It's a little bashy to it's not a little, it's really bashy to write that solution to this.
All right, on to applications.
Do you think we should do number 1 or do it? I think it's just like skip it.
Number 1, I think you should still do it.
Okay. Is there a better way to do it than just like try all of them?
The roots of, bruh, the multiples of roots of unity. That simplifies calculator.
Oh,
Oh, I just gave out a hint, but whatever.
yeah, because these can be written like that. And
Number C is
can be
you guys
written
like, I don't know. Wait, you guys should do this. Never mind. Do you guys recognize what answer choice C is?
oh, this is just like 45 degrees, right?
Yeah, it's a. When in doubt, you
Or
can just
no, it's not 45 degrees because the cosine is negative. So what, negative? Wait, stop.
135.
We got 135 degrees. This
Hey,
is this.
now I'm the one teaching you. Mohahaha.
Huh?
Nothing.
That's what I thought.
What you thought?
No, I erased it. And these should just be pretty basic. I'm pretty sure the answer is, let me think. This is like 1/2, I think. And this is. And that probably wouldn't be something nice. And this is easily just like 0 for the real part, and this is -32. So if you just like try it and use the roots of unity to like make it better, the answer is just B. That
Okay.
makes sense?
All right, on to problem 2. Wait, should you be presenting applications, or do you just? Or,
I
like,
don't really mind. I feel like we're just like doing everything together anyway.
Yeah.
And I think it's easier for me because I get to annotate.
Wait, number 2. I don't know. It's pretty interesting. Oh wait, never mind. I just realized.
It's just like the same thing with Vietas and with this condition.
Oh yeah. Oh wait, do you teach them that conjugate is preserved usually?
The what?
Yeah. Wait. Because like for example, wait. So this is to everybody. Like A conjugate plus B conjugate is equal to conjugate of A plus B. A conjugate times times B conjugate is AB conjugate. So like usually like conjugate is preserved through like many different operations.
Okay, yeah, that makes sense. Because it's just like something subtracted by. Wait, no, this actually like makes sense a lot because the conjugate can just be like C plus D I, because C minus DI isn't really defined very well because D can be negative, and that's listed as C plus DI. And if it's preserved like with regular multiplication of complex numbers, it should just be preserved. I don't know what I'm saying, but yeah, if you just try it, it is preserved. And that makes sense, like theoretically, I guess. Wait, 3 is like way easier. If we just multiply by z, then we just get like z to 6 equals 1. And that's just 6 solutions. Is that actually this answer? Wait, no, it's not the answer.
I don't think so. That's not correct.
Oh, because no, because
Completely incorrect.
Wait. Why would I be?
Wait, it's equal to the magnitude of z squared.
Yeah, wait, sorry.
All the
Wait, no, but this is just like the magnitude of this term is just like. Oh wait, what am I? Let me think.
There is not 6.
This is like the magnitude of z cubed, like the distance from the origin. Like you could take the magnitude on both sides, kind of. And
like
then like
this is important here, and then you have to do something else.
no, so you just have like the magnitude of z cubed is equal to like 1 or 0. Oh, sorry, it's equal to the magnitude of z squared.
Why?
Because we can just okay, wait, let me explain this better. I think I'm cooking. So z6 is equal to the magnitude of z squared. We can take magnitudes on both sides. The magnitude of z6 is equal to the magnitude of z squared. And since this is a real number, we could just say this is just magnitude of z squared. And the magnitude of z to the 6 is just equal to the magnitude of z to cubed, z cubed. Because like this is like the square root of like this z to the 6th power and stuff. And this is just like.
Wait, can you just say the left hand side has magnitude z5 and the right hand side has magnitude z? And so that means the magnitude of z to the 5th is equal to the magnitude of z.
Okay, yeah, that's I think that's much
So
better.
it's 1 or 0 because magnitude is positive real.
Yeah, so the magnitude of z to the 5th is the same as the magnitude of z. So we just have the magnitude And that's the same as magnitude of z because that's like conjugate is only flipping the sign of the imaginary part, so the magnitude remains the same. And so you just have like the magnitude of z fifth equals magnitude of z. So wait, Andy, you can just like do the rest. My brain is spasming.
So and so afterwards, right? It's since like z magnitude, so it's either 1 or 0. If it's magnitude 0, then the number is clearly 0 because there's nothing else. If it's 1, then you get let the argument be data. Then you have CIS of 5 data is you CIS negative data. So like you get multiples of 2 pi. And then like wait. Yeah. And so afterwards you get that it's just the 6 roots of unity, I believe. And so yeah, Eric, you should get better. And so
Yeah,
there's
I think so.
1, which is 7.
Wait, I think this is like a real. I think we took this from like a real concept. Let me show you the solution there. This is really sad. Wait, yeah, I think it's just 7 as well. Yeah.
Anyways, next question, you guys better do it.
Yeah, wait. I want to like search this up. But I also want to move on to like really fun bonus problem because it's just very very fun. And the only reason it's fun is because Andy didn't want it to be there. So, what are these? I think these are like AIME number 9s. They shouldn't be too bad, but they are harder than the rest of them. And for this bonus problem, I was just taking ARMO local, and the 10th problem was just like a very nice complex number problem, and so I just put it here. I don't exactly remember the wording, so it's reworded. And the 3 bonus stars aren't really meant to signify difficulty; they're just like bonus stars because it's a bonus section. And basically, the first thing we can notice about the 7th power of all roots is of this polynomial is that this can be factored into z cubed minus I and z to the 7th minus I. It's actually kind of sad because during the contest I didn't even notice this, so I was just kind of cooked. But I put enough effort into knowing the solution that I really want to share it now. So we want the 7th power of all roots here that have a positive imaginary part. And we can think of this as just like I times the 7th, 3rd, and negative I times the 3rd and 7th roots of unity. Because when we have negative I to like the cubed is equal to I. So if we just have like negative I times e to the 2 pi I over 3 cubed, it just be like 1 times negative I cubed, which is equal to I. So z cubed minus I is equal to 0. And now we just want all of these that have a positive imaginary part. So negative I times e to the 2 pi I n over 3 and e to the I times negative I times e to the 2 pi I n over 7. These have a positive imaginary part. So we want these terms to have a I think negative real part. Sorry, I was misreading the problem. Because when we multiply this by negative I, then we'll just have a positive imaginary part. And now this is a part of the problem where we can like think of this and graph it out. So for this is the 3rd roots, and this is like the 7th roots. I'm gonna butcher this drawing, but it'll be okay. It's like something like this. So when it's in the 3rd root case and it has a negative real part, we have these 2 roots that work. And we'll have the negative real part for the 7th root case. Then there's 4 roots that work. And now we can find the sum of the 7th powers. Now the sum of the 7th powers of like some roots of unity are gonna be really bad. But thank goodness that this is exactly we have z to the 7th minus I equals 0. So the sum of the 7th powers of these 4 is just gonna be exactly I 4 times. So for this part of the problem, we just have the sum of, well, I'm gonna box this 4i. And now we just work with the z cubed minus I part. And for these two roots, we have to find the sum of the 7 powers of them. And this is just equal to z cubed squared times z. And that is just -1 times z. And this is like, as Andy said, -1/2 plus √3/2i. And -1/2 minus √3/2i times I, negative I, respectively. And we can see that the real parts will just cancel out here because it's just a -1. So, sorry. So because these are just like flipped signs. So when we add these two, we just have like the -1 times. So we're adding the two solutions we have together as their 7th power. So it's -1 times -1/2 I plus 1/2 I. Wait. Oh, this should be negative here. That's why I'm tripping. Okay, so it's plus 1/2 I plus 1/2 I, and that's just -I. So the sum for this case is just going to be -I. So when we add them together, we have a final answer of 3i, which is just 4i minus I. So does that make sense? I know it's a pretty hard problem, and we just explained what like basic complex numbers is, and then we just like jumped into like a very difficult application. But I feel that to have some strong problem, like basic foundation in complex numbers is important. And to just like experiment with harder problems is just how you get like familiar with the concept as a whole. Does this solution make sense? I'm now just looking back into how messy this work was. Yeah, basically, if I can summarize it, you just base this factorization first. That's the first thing important to notice. And we can use some like diagramming to help us determine which roots here satisfy the positive imaginary parts part. And then we can use the definitions given in these factors to find the 7 powers. And when you add them, we get a nice answer of 3i at the end. Wait, what do you mean the quadrant of the mini graphs are not correct? Wait. No, it does, because when for these, we just need a negative real part, because we're multiplying these at the end by -I. Because we have it here that it's -I times the 7th derivative unity. I've graphed out the 7th derivative unity. We know that the -I times that has a negative real part. Sorry, has a positive imaginary part. So we just want the ones that have a negative real part, and that's what these are. Because we're multiplying these by -I at the end. Because we have this like as negative I term here that just like makes us do that. So when we multiply these by -I, we make it work out. Yeah, awesome. Is our time up at 8:30? Andy,
Huh?
is our time up at 8:30?
I have no clue.
Does anybody know? Okay, my mom is saying yes. Awesome. So if you want to stick around, I have nothing to do. So
I want to
Yeah.
stick around.
you want to stick around? Shreyas wants to stick around.
Yes,
Okay.
I'll
Anyone
stick-
else wants to spend their like another hour of their life going over hard AIME problems? But yeah, other than that, I think that's good. I hope you learned something, or if you didn't, I hope you began to learn something, which is how I learned about complex numbers myself.
I learned a lot.
Thank you, Shreyas. Yeah, thank you for all for coming. I know it's the last class, so it's like a bit of a bittersweet moment, but I've only been here. This is the only class I've been teaching, so Yeah, thanks guys. Goodbye.
You know, it's probably a sweet moment for everyone, bro.
I think Shreya should stop talking and I should forcibly mute
I
him.
agree. That is.
My bad.
I do you want to do you wait? Already continue talking, Eric?
Huh?
Wait, so we'll continue discussing problems, right?
If you want to stick around, yeah. I'm afraid that like the people that are sticking around are just like watching a YouTube video and like just like didn't realize that the
That's
class
me.
is over. Honestly, that'd be me as well. But sure, we can like
Hey, Vincent, are you here?
yeah, we should do a roll call.
Yan Huang, are you here?
Oh my god.
Bro is not here. Bro is watching YouTube.
Yo,
There-
what?
I bet half the people in this call are watching YouTube.
Yan Huang, hello, Yan Huang.
Wait,
I
Andy,
know.
Andy, do you want to try
I
like
think
maybe
it's the
4 or
time for us
5?
to stop recording and the time to end the class. I think it's already 8:31, right?
Yeah.
Mhm.
Like we can still discuss problems, right?
Yeah, but you need to stop recording. Yeah, Eric.
Okay,
Yeah.
wait. I can stop recording, yeah.
Alright. We should just cut out the end of the recording because it's just us discussing random stuff.
Dude, I thought that was a student. That's my bad, chat.
Bro, you're actually like wait, where's my request to record? Oh my god, wait, please don't tell me there's no
Aiden D, are you here? Good, very good.
wait, where do I access the recording? I'm very confused. It does say recording, right? Did I stop the screen share? Who's recording?
Just stop the recording. Oh wait.
Where?
Yeah. Oh yeah. No. Alex, Mama.
Uh-huh.
How do you hit that record?
Eric did the
Oh
recording.
wait, I think I see
Oh
it.
wait. Never mind.
Yeah, he